So, hello. The aim of this presentation is to give you an idea of current capabilities of techniques for sound velocity measurement, in particular focusing on iron and iron-nickel alloys at high pressure and high temperature, so discussing what kind of a mineral physics constraint can we put from this measurement to the composition of the Earth's inner core. But let's just put something, oops, that's not mine. Okay, let's, anyhow, the message of the previous slide that didn't come well was just to say that from an experimental point of view, now there is a compelling evidence that the stable phase for pure iron at the condition of the Earth's inner core is ACP. And there is an increasing number of diamond anvil cell X-ray diffraction experiment that suggests that even inclusion of silicon and nickel up to reasonable amount don't change this conclusion. From an experimental mineral physics point of view, the ACP phase of iron is the one expected stable. So in the following, I will just discuss sound velocity on ACP phases. But more in general, how do we probe the Earth's interiors? Well, without having to drill too much. Direct sampling exists only for the crust, upper mantle, and in case of deep origin diamond, it's been speculated to come from the lower mantle. But for the innermost part of our planet, in particular the core, there doesn't exist a direct sampling. So we have to rely on remote sensing. And as we have seen in the previous talk, seismology is definitely the most precious tool we have. It provides information from starting from body waves, free oscillation mode, on density, elasticity, sound velocities, and compressibility of the Earth's interior. As we have heard before, the kind of information we can get from seismology is very rich. Here in the following, I will just simplify them considering a radial average model. So just one-dimensional radial seismic profile, like the here present PREM model. Basically, we will consider the evolution with pressure or with depth of a compressional sound velocity Vp, shear sound velocity Vs, and density. We heard about this a bit. What I'm going to present here is the second half of the story. Basically, the elasticity of mineral. Because to derive accurate compositional model, we have to try to answer this leading question proposed by Birch in the early 50s. What material might have the elastic properties demonstrated by seismic wave under the condition of the Earth's interior? And to be fair, I have to state that in the same paper, Birch also said that unaware readers should take warning that ordinary language undergoes modification to a high-pressure form when applied to the interior. Here there are examples of this translation. So for what concerns my talk, whenever I say pure iron, feel free to understand a certain mixture of all the elements. Okay, but back to science. Starting from shock wave measurement and looking at velocities versus density systematics for several elements, Birch suggested the iron to be the main constituent of the Earth's interior. Now, from cosmochemical abundance, we know that nickel has to be present and alloy to iron up to a few weight %. But at first approximation, the inclusion of nickel does not significantly change the elastic properties of iron. However, a closer look to the equation of state of iron with respect to what observed by seismic model, and here comparing the density as a function of pressure, highlight a quite significant density difference. Either in the outer core and the inner core, ACP iron is too dense with respect to seismic observation, and this is irrespective of possible temperature correction. So this observation provides a direct and a quite compelling argument for the presence of a light element alloyed with iron in the core. And taking after Poirier, for example, we can include as most likely candidate silicon, sulfur, oxygen, and carbon. So it becomes evident the logic of performing sound velocity measurement on iron and iron alloys as a function of pressure and temperature. However, performing elasticity measurement even at ambient condition is quite challenging, and traditional techniques such as ultrasonic investigation, Brillouin measurement, all exhibit some limitation, be this on the highest attainable pressure. This is, for example, the case for inelastic neutron scattering measurement or ultrasonic measurement, where the probe or sample dimension imply the use of large volume press, so the limit on the pressure we can reach. Other limitation comes from the choice of sample. Brillouin measurement and, in general, optical measurement are limited to transparent sample. In the case of metallic opaque alloy, so it's particularly critical. Partial information, for example, can be derived from Raman spectroscopy or from surface probe. Other techniques like radial diffraction involve quite complex approximation, so that basically all these technical difficulties prevent measurement of sound velocity on iron and alloys at megabar condition up to the beginning of 2000, where two major technological advances allowed this measurement. The first is the third generation synchrotron source, and the second is the diamond anvil-set technology. So thanks to the brilliance of third generation synchrotron source, sample with volume smaller than 10 to minus 5 cubic millimeter can be probed. And basically, irrespective of the technique, X-ray beam can be focused down to 100 micron, and for many techniques even below 10 micron, thus allowing the use of a diamond anvil cell. The idea of this high pressure genetic device is pretty simple and quite neat. Two diamond anvils are cut with the parallel surface, and the sample is pressurized between the two anvils and a metallic gasket. Now the hardness of diamond is such that the ratio between the upper and the lower surface can be quite high. Typically we are speaking of 4 millimeter over here and below 100 micron the culate. So for a moderate, well, relatively moderate force on the upper culate, upper surface, we can have quite high pressure here. And to give a feeling, for a pressure about 100 bar here, we might end up with pressure of 1 million bar here, so megabar, 100 GPa. And for what concern sound velocity measurement, in the early 2000s, two techniques emerged as suitable for this kind of measurement. The first, mostly developed in Grenoble at the TSRF, is momentum resolved inelastic X-ray scattering. The second, mostly developed in Chicago at APS, is nuclear resonant inelastic X-ray scattering. And I'm sorry, but the graph here are not coming correct. All the PDF are not working. But anyhow, I was just going to show two data sets that arrived in science paper, one shortly after the other. One by inelastic neutron scattering and the second by nuclear resonant inelastic X-ray scattering. This work really opened in 2001 the possibility of high pressure measurement and sound velocity measurement at megabar pressure. And they generate big interest, especially because one work by Chiquet and co-workers suggested iron velocity be lower so that we need to add light element to match the seismic observation, while the work of Mao and co-worker had an opposite conclusion. But to understand a bit that the differences and complementarity of this technique, I was going to open a parenthesis on these two techniques, and once again, you're not coming the graph. But anyhow, the idea of nuclear resonant inelastic X-ray scattering is that techniques exploit the secondary photoemission from the resonance of Mossbauer isotopes, in the specific case iron-57, to obtain information on the phonon density of state. And giving a series of approximation from a parabolic fit to the low energy of the phonon dispersion, we can get the mean Debye velocity, which, combined with the equation of state, gives the compression sound velocity Vp and the shear sound velocity Vs. So, as you can see, this technique involves some degree of approximation. It's rich in information in the sense that from integration of phonon density of state, many thermodynamic parameters can be derived. But if we just stay with the case of sound velocities, in practice what we can say is that determination of Vs is quite insensitive of the different approximation involved in the use of different equation of state necessary in the technique, while this is not the case of Vs. The other technique in elastic X-ray scattering is a conceptually simple technique. It's a photon in, photon out technique where a photon of well-defined energy, momentum, and polarization is scattered by the sample into a second photon of well-defined energy, momentum, and polarization. And given the energy and momentum conservation law, the difference between the outcoming and incoming energy and outcoming and incoming momentum is the energy and momentum transferred to the system. So basically, performing a directional analysis of the scattered photon to the scattering angle, we can get information of Q, and from the analysis of the scattered photon, the energy of E. This technique can be applied to a large variety of samples, be this metal or semiconductor, opaque or transparent, be this single crystal, powder, or liquid. So if we just want to limit to the case of elasticity, the research source of information comes from single crystal, where the complete photon dispersion curve can be determined, and the full elastic tensor without any approximation or a priori model. However, for what concerns the following of this presentation, and typically experimental megabar pressure, experiments are being limited to the case of powders. This is either because it's more complicated to preserve a single crystal at such elevated pressure, and in the specific case of iron, the BCC to ACP transition that iron undergoes around 13 GPa prevent keeping single crystal phase even starting from single crystal BCC. And in the case of polycrystalline sample, what is probed is an average longitudinal photon dispersion. Here are examples of the raw data that are characterized by an elastic scattering at zero energy, a peak of the photon excitation of the sample, in this case iron, and the two transverse and longitudinal photon excitation of the diamond needles. So repeating this measurement, determining from the position of this peak as a function of the angle, or if you want, the exchange momentum Q, what we get is the aggregate photon dispersion that within a lattice-Von-Karman approximation, if you just consider first-order interaction, can be well described by sinus fit, and the compression sound velocity Vp is just the slope of the initial part of the dispersion. And then if we use a bulk modulus, as for example determined from diffraction, we can get the shear velocity as well. So with this in mind, we can go back to another problem and look at inelastic X-ray scattering on pure iron. Here you can just see a little bit of what I wanted to show. That was the compressional velocity as a function of density. The inelastic measurement under static condition by XS are this open symbol. You can just see one of the shock wave measurement. Here the idea is to say that the measurement performed under the static pressure well compared with the dynamic data, and they all plot into a line when plotted as a function of density. This on one side supports the validity, at least a first order approximation of the Birch law, so a linear dependence of the compression of velocity on density or volume irrespective of the specific volume and temperature condition. That is something that can be understood in the framework of a quasi-harmonic approximation. Furthermore, this extrapolation, and this is the part that unfortunately you cannot see, extrapolate lower than the velocity of the prem. So that again brings argument in favor of the presence of element lighter than iron. Following study, that this time fortunately I can plot, have been performed. Here you can see what I was showing before. These are the black dots are the static data, the red are the shock, they plot on a line, and the extrapolation is below prem. So the following studies start looking at the velocity on iron compounds, iron alloyed with this light element. And here I'm plotting FESI, FEO, FES, and FES2. As you can see, no one of these go through to prem. Few years after, and this I cannot see, but basically the measurement have been repeated even in the case of FE3C, which plot about here. But again, none of these go through the prem. But starting from this kind of observation, a model has been put forward, which basically suggests that the sulfur not possible to be as a main element in the core. And if in the following, just following with the inner core, this, the combination of this measurement on end member suggests the preferential core composition with about 2% of silicon and a minor trace of oxygen. However, this kind of result have been based on a series of assumptions. The already discussed validity of the Birch law, a linear mixing of velocities of an end member compound, Furthermore, the inclusion up to 15 weight% of nickel was considered negligible. And what was, up to me, one of the major limitations is that the constraints were coming only from looking VP and rho, neglecting the third parameter, important parameter that we can measure from seismic model, that is VS. So the next natural step was start performing sound velocity, VP and VS, together with density determination on iron-nickel silicon alloy of a suitable composition for the Earth's core, plus checking the iron as a fundamental reference for all our comparison. And I will start with this point first. Okay, here I'm plotting the compressional velocity VP as a function of density as obtained by different techniques. Luckily here you can see all the things that was not possible to show before. From the original paper, Henrik's measurement by Mao and co-worker, Fiquet, and following measurement done by these two techniques over the last 10 years. Once plotted as a function of density and once used for the analysis of the Henrik's data, suitable non-hydrostatic equation of state, all the data plot overall on a straight line and compare overall favorably. Maybe partial exception can be this point that was the one driving a bit the extrapolation up. But anyhow, we can feel confident of this result. And this open symbol measurement we took recently over this year, which still stay there. So positive, we have a reference value for iron, and we can see what happened when alloying nickel and silicon. So we look at a polycrystalline homogeneous sample of a silicon-bearing iron-nickel alloy prepared by a pressure, temperature, interdiffusion and piston cylinder press, and the chemical composition was determined by electron microprobe analysis. And the data I'm going to show you are for sample containing 3.7 weight% of silicon and 4.3 weight% of nickel. Compacted pellet of suitable dimension have been loaded into diamond anvil cell, and the example of the aggregate phonon dispersion collected for increasing density are here reported. We constrain the aggregate dispersion in the first brilliant zone by 8 to 9 Q point, and we derived from a sinus fit to the data VP with typical determination around 2%. From parallel diffraction measurement, we had the phase stability, phase purity, and most importantly, density. And comparing these two, we can get information on VS as well. And if we do this, this is what we get. And in particular, I'm comparing the result on this iron-nickel alloy together with the result of pure iron and on iron-nickel alloy. As you can see, result on pure iron and our iron-nickel over the investigated pressure range quite well overlap, at least they're within the experimental scattering, while adding 3.7 weight% of silicon makes the sound velocity systematically faster, as better highlighted by the linear fit to data. This difference is about 9%. The notion that the sound velocity increase is solely due to the presence of silicon is further supported by a good comparison, a good agreement between our result and ab initio calculation on a FESI sample about the same silicon content, this open symbol, that are in quite good agreement with other result. So now we can see what happens if we extrapolate this trend to the density of the core. And here are the results. This is the PREM model, and as originally suggested by Fiquet and co-worker, pure iron extrapolate lower than PREM. Adding 3.7 weight% of silicon make it too fast. But this time we have two data sets that bracket the sound, the velocity of the PREM. So we can play with a linear mixing model, and we end up with values straddling the PREM for a silicon content about 1.2 weight%. So far so good. But what about VS? And here is where comes the problem. As you can see, both pure iron and iron-nickel silicon alloy has sound velocity significantly faster than PREM. And at this point, it's clear that we cannot play with the silicon content to bring these things down. So we need to look for something else, and is the effect of high temperature. Anharmonic high temperature effects were suggested in a figure that is not here plotted by nuclear resonant and elastic X-ray measurement performed on laser heated sample. This time the sample is compressed into a diamond anvil cell and heated by 2 laser beam. This is the technique I was describing you before, where the phonon density of state was measured and then the bi-velocity. This technique indicated a softening, a constant density, both for VP and VS. However, the complex data treatment involved, the highly reliance on external PVT equation of state, that in case of iron are particularly critical because different studies do not agree completely, bring doubt on the validity of this result. Furthermore, there has not been nor density or phase determination during this measurement, and another argument that was brought up was that the analysis for this data involved an harmonic model to ultimately argue for non-harmonic approximation. So we asked ourselves if there was a more direct way to probe temperature effect on some velocity, and at least for VP, the answer is yes. We can use inelastic X-ray scattering, again, polycrystalline sample, so what is probed is the aggregate phonon dispersion and directly VP, and in parallel, X-ray diffraction measurement to check stability, phase purity, and density. In this kind of experiment, given the need of a long exposure time and the need of a stable, uniform heating, have been done by resistive heating, either putting micro-machined furnace just around the anvils, either applying, and that was going to be shown here, but it's not appearing, directly applying a DC voltage on the iron sample. Through platinum lead, we are bringing current to the sample that is heated by ohmic effect. Results have been collected in the 30 to 93 GPa range, 300 to 1100 K, all in the ACP phase. And here are the results that once plotted as a function of density follow the same trend that those indicated by ambient temperature result. And this is irrespective of the temperature, thus suggesting that non-harmonic high temperature effects are negligible at least up to 1100 K, and that VP scale linearly with density irrespective of the specific pressure and temperature condition. The softening expected by the work of Lin and co-worker, I was not able to show you before, I just described, suggests a softening along this line. And as you can see, that is quite out between, even considering error bars and even at the lowest compression where potential and harmonic effects are expected to be more relevant. However, the temperature of the core is not 1100. So for that, depending on model, the temperature are supposed to be between 4,000 and 7,000 Kelvin, where all ab initio calculations suggest an harmonic effect. Different calculation might give different amount, but they all tend to agree that this can be particularly relevant on the shear velocity, especially for temperature approaching the melting. As such, we decided to correct our result for an harmonic correction at a constant density of 13,000 kilogram over cubic millimeter, taking a 4% softening on VP and 30% of softening on VS at 5,000 Kelvin. This correction comes from a work of Vocciadlo and co-worker. Probably she's going to speak a bit more in detail of that after a correction for the density variation, because here I just want to look at effect, an harmonic effect at constant density. And if we add this other ingredient in our minimization, we end up with these two green dots. So we have a solution to the main seismic observable, the seismic wave speed, both VP and VS, and density for a model composition of 1.5 weight% of silicon at 5,000 Kelvin. So, getting to the conclusion was quick without figure. The overall evidence from mineral physics measurement on sound velocities support silicon as the major light element in the inner core. And specifically, we can suggest an inner core model containing 4 to 5 weight% of nickel and 1 to 2 weight% of silicon. Unfortunately, this is not a unique solution because the exact amount of silicon depend on the amount of temperature correction. There is clearly a compensation effect between temperature and silicon. Higher is the temperature, more silicon you can put. But assuming a reasonable, an harmonic correction taken from a Benizio calculation, we end up with this result. As well can be partially affected if other light elements are present. But however, if we take the Lichter's value of partition coefficient for silicon between liquid and solid iron, so that we can estimate the silicon amount on the outer core and then a total core amount of silicon, we end up with a total core composition with a silicon amount ranging between 1.2 and 4 weight%, which is on the lower range of core formation and core interaction model that typically call for larger amount of silicon in the core. Here the bottom message is we cannot have 10 weight% of silicon in the core. That would result in too high sound velocity with respect to the seismic observation. Obviously, this model is quite simple, but in this simplicity is able to capture, to match the density, P wave and S wave velocity, only considering silicon amount, silicon inclusion, and reasonable temperature correction. In the past, other more exotic mechanisms have been suggested to explain this low value of Vs. That could go from the presence of partial melting in the core, either viscoelastic relaxation, or a bit on the line what was presenting Annie this morning, anisotropic patches that effectively lower the Vs. What I'm suggesting is that these mechanisms are not strictly needed just to explain the absolute value of seismic velocity. Most likely, they are needed to account for the seismic complexity the previous speaker discussed, be this seismic attenuation, seismic anisotropy, variation with depth, hemisphericity. All these properties call for single crystalline-like properties beyond the radial simple model here presented. And attempt along this direction has been done. In the case of iron, the big problem was the lack of availability of the iron in the ACP phase as a single crystal. But one trick we can play is to press the sample without pressure transmitting medium, forcing uniaxial stress and developing preferential orientation of the C-axis of the hexagonal crystal along the main compression axis of the cell, so that playing with the cell geometry, we can mainly probe different direction. Doing this exercise, we get up to 3% seismic sound velocity difference, so the order of the seismic anisotropy. However, this kind of approach have an intrinsic limit in the pressure you can achieve, because as soon as the phonon of iron reach the one of diamond, the more intense phonon of diamond will stop that. This is not going to be the case instead for single crystalline measurement, where, as mentioned already, we can go to higher brilliance zone, so get rid of the problem of diamond, and we can get the full phonon dispersion, measuring all the single crystalline elastic constant. In case of analogous material, cobalt, for example, measurement have been done up to 40 GPa and 1000 Kelvin. This is still pressure well below the one of the inner core. But the good thing is that so far this kind of investigation has been only limited by sample availability, dimension, and sample quality, so that working on this aspect, there is not an intrinsic limit on this kind of measurement. You just need to get there and make a good small sample. And let me conclude acknowledging the people, my closest collaboration for the work I've been showing: James Badro, Guillaume Fiquet, Guillaume Morare, Julien Siebert in Paris, Ferrano Celli at CAA, Michael Krisch at SRF in Grenoble, Chantal Arachni, Dan Farber, Rick Ryerson, and Dave Ruddle in Livermore, Fei at the Geophysical Lab in Washington, and Tetsu Kobayashi at Tokyo Tech. And as well, I need to acknowledge funding agency that supported this study. And I thank you for your listening and apologize for the figure that didn't come well.